In this video, we're going to look at the binomial distribution in action. One of the things I've noticed over the years is that you can teach people about the binomial, and then you can put some examples in front of them and ask them whether the binomial applies or not, and people have a hard time identifying whether it can be used or not. And so that's the first thing that we're going to tackle in this series on the binomial here. So you may want to jot this down. You may want to have this in your notes or something, but you can only apply the binomial distribution to an application if you have 4 different conditions that are satisfied. And so they are summarized for you here on this slide. You need to have a fixed number of independent trials with binary outcomes and a fixed probability of success. And so what I would suggest for most people is when you're getting started studying this particular part of the text, it wouldn't be a bad idea if you had like a checklist you ran down. You know, as you go through an example, you just make sure that you check off each of these conditions. And if you can, then you can use the binomial. So to help you with this, we have a couple of examples that we're going to pull from the text. We're going to run through this series of examples that you can see on the screen in front of you right now. We'll do the even exercises here. So number 10, number 12, number 14, and then there's an additional one on the next page. And so again, what I would suggest is when you tackle one of these, you want to have a checklist. Do you have a fixed number of independent trials with binary outcomes? And if so, what are those binary outcomes? And what is the probability of success, as we would call it? And so for starters, let's take a look at number 10 here. It says a poll of 1,200 registered voters is conducted in which the respondents are asked whether they believe Congress should reform Social Security. And the instructions are clear. They're saying basically, hey, can you use a binomial here or not? And so let's write down our little checklist. So do we have a fixed number of trials? Well, we do, because the problem said there were 1,200 in the poll. So I'm writing that down. And then the next thing they're asking is, are they independent trials? Let's continue our checklist. Are the trials independent? Well, let's go back and look at the problem here. If you'll notice, it doesn't explicitly say that we have independent trials, but it says we have a poll of 1,200 registered voters. And so I'm going to assume that this is a properly conducted poll. In other words, it was done by some kind of a polling firm, and it was a random selection, because otherwise the poll wouldn't be a good poll. And so since we can safely assume that we do have a random sample here of registered voters, I would say yes, we do have independence, even though it doesn't explicitly state it. So let's put that down. So again, do we have binary outcomes? Well, you can go back and look at the problem again. And it says that the voters were asked whether they believe that Congress should reform Social Security. And so if you think about how they would answer that question, basically it's a yes or no answer. And so if we assume that that's the case, then we do have binary outcomes. And then finally, we want to make sure that we have a fixed probability of success, as we would call it. So in other words, the probabilities assigned to the 2 binary outcomes, are they fixed or are they not? So let's go back and take a look at the problem again. So I'm reading the problem here, and it doesn't explicitly say that a certain proportion of individuals believe that Congress should reform Social Security, but it's like they say on TV, the truth is out there. So in other words, I'm assuming that there is a certain proportion of the population that thinks Congress should reform Social Security, and there's a certain proportion that thinks they shouldn't. And even though I may not know what those proportions are, and they, are probably very hard to determine, I think that that's a fixed value. And so, at least for the purpose of this problem, I'm going to say yes, we do have a fixed probability of success, and so that means that we could use a binomial model for number 10. And so that would be my answer to that question. And so regarding whether or not we can use the binomial, again, just to be clear, I would answer yes. Now, we're not suggesting that every single time you look at some application of the binomial that you have to write at such length. But what I'm suggesting effectively is that when you look at a particular situation and you're wondering, can I use a binomial here or not, you may want to mentally go through this checklist. And so that's why you'd want to have it on your notes. Let's take a look at the next example. Let's look at the next example here. I'm going to use number 12, and it says 3 cards are selected from a standard 52 card deck with replacement. The number of kings selected is recorded. Okay, so regarding the phrase that says with replacement, let's be clear on what that means. That means that when you're looking at this deck of cards, picture it in your mind, and you reach to the deck and you take a card out and you look at the card. With replacement means you're going to put the card back in the deck, and presumably the cards would then be shuffled. And so in other words, every time a card is drawn, there's 52 cards in the deck. And so that's going to be important for this particular problem. But let's run down our checklist and see what we have here. So again, I'm checking that I have a fixed number of independent trials with binary outcomes and a fixed probability of success. And so I want to go through this and look carefully to see if I can get that out of it. Now the problem said that we're going to repeat the experiment 3 times. And so that would be a fixed number of trials. And that means I can check off the first condition. The problem also said that we're replacing the cards as we draw them and look at them, put them back in the deck. And so that would mean that the trials are independent because the probability of obtaining a card, a certain card, a king in this case, isn't going to change from one trial to the next. So we do have independence as well, and I'll check that off. Now the third item is that we have binary outcomes. And so again, if you go back and look at the problem, it says 3 cards are selected from a standard 52 card deck with replacement. The number of kings selected is recorded. So in this case, we either have a king or we don't. And so that is our binary outcomes right there. And so we can also check that off. And then the final condition, we want to make sure that we have a fixed probability of success. So keep in mind, we're defining success as obtaining a king each time we pull a card. So the probability of drawing a king from the deck each time is fixed because there's going to be 4 kings in the deck, and we're replacing every time we draw a card. So we also have a fixed probability of success, and all 4 conditions are satisfied, and so the binomial model would apply here as well. Let's look at the next example. Number 14 says, a baseball player who reaches base safely 30% of the time is allowed to bat until he reaches base safely for the 3rd time. The number of at-bats required is recorded. Okay, so again, we're wanting to make sure that we have a fixed number of independent trials with binary outcomes and a fixed probability of success. And so let's make our checklist. So first up, do we have a fixed number of trials? Let's look at the problem again. The problem says a baseball player who reaches base safely 30% of the time is allowed to bat until he reaches base safely for the 3rd time. And so if you think about that, that is effectively saying that there is not going to be a fixed number of trials. Consider this. What I'm suggesting with the little diagram that I've drawn there off to the side is that the first time we tried this, the player reached base safely each time he batted. But the second time we did this, he didn't make it to the base the first time, and then in order to get three arrivals safely at base, it took 4 trials. And so in that case, it's plain to see that the number of trials is not going to be fixed, and so we can't use a binomial model here. So let's put that down. Okay, let's take a look at our next example. I'm using problem number 16 here, and this one is a little bit more subtle. You have to think very carefully about this. So it says, in a town with 400 citizens, 100 randomly selected citizens are asked to identify their religion. The number who identify with a Christian religion is recorded. And so again, we're looking for a fixed number of independent trials with binary outcomes and a fixed probability of success. Now, at first glance, you might look at this and think, well, that's easy. All 4 conditions are satisfied. This is definitely a binomial. But if you reflect more carefully, especially regarding independence, I would suggest to you that we don't actually have independence here. So I'm not expecting you to know this, but you'll see later that one of the conditions that we frequently apply when we're doing some kind of a probability experiment, when we're doing a hypothesis test, for example, we want to maintain independence. And when we do that, we require that our sample size never exceed 5% of the population. And the reason for that is because when you exceed that, you tend to lose independence. And so then that becomes an issue. Now here, it says plainly that we have a town with 400 citizens and we sampled 100 of them. Now think about how a small town would be typically. Are we expecting that this small town of 400 people is all 400 completely unrelated single people? Or would we expect that in this small town of 400 people that there's a good number of families? And I would say, well, according to my experience, in this type of environment, I would expect that this is a town with families. And there may be a few single people in there, but by and large, I would expect a significant number of families. And I think about this, and I think to myself, have I ever met a family where, they have a good number of people in the family, and you have like a Christian and a Jew and a Muslim and a Buddhist and a Hindu and all of these different religions in one family? And in my experience, I would say, well, absolutely not. Most of the time when you see a family, there tends to be a certain amount of homogeneity with regard to religion in the family. Everybody is Catholic or everybody is Jewish or something like that. And so you don't see a family where everybody independently chooses their religion. And so in response to this particular question here, if you work your way down the checklist, it is independence that we don't have. And if you want to answer it succinctly, you could say, well, we don't have independence because the sample is too large. And that's a problem here. We're sampling 25% of the population. So as you can see, I have my answer down here at the bottom. With regard to the first condition, do we have a fixed number of trials? We do. There's 100. With regard to the second condition, are they independent? And we would say no, they're not independent. And again, it's because the sample is too large. We sampled 25% of the population, which is not good. And for that reason, the binomial model does not apply. I hope that's been helpful, and if you have any questions about this, feel free to drop me a line. Otherwise, go on to the next video and we'll look at some actual problems involving the binomial distribution.